Alright, welcome to another AQA A-level chemistry video. Today I'm going to be doing a video on carbon-13 NMR. This is actually the second time I went through this, but the first time the audio wasn't on. So I'm quite annoyed that it didn't happen, but it is what it is. We've got to move on now. So if you see some highlighting that's already there, that's because I already went through this. But yeah, I'm going to go through this topic quite quickly because this is quite a straightforward video. So the first type of NMR that we should look at is carbon-13 NMR. And this is slightly more simple than hydrogen-1 NMR, because with hydrogen-1 NMR, you have to learn about splitting, ratios. So it's a bit more complex compared to carbon-13 NMR, where you're just looking at the peaks and that's pretty much it, and then looking at your data sheet and then deciding from there. Now, I know you're probably thinking that because it's easier, it's probably better for you, but I mean, yes, in the exam, technically, it's going to be better for you because it's less complex. You're just looking at where the peaks are. But in hindsight, you want it to be a bit more. You want the reason why it's complex because there's more detail, and when there's more detail with the NMR, it's usually because it gives you a bit more. When it's more complex, it gives you more detail. And if there's more detail, it makes sure that it makes it easier for you to determine what the structure of your compound is, rather than just what type of bonds there are. So that's why hydrogen one is a is in a long term. If you actually sit in your exam, hydrogen one NMR is actually probably better for you to actually use to determine what type of molecule you have, because you can know which type of the environment of hydrogens that are in your compound, and be able to better suit which part of a molecule is bonding to which. So that's why I kind of think that's why hydrogen one is a bit better, because it gives you, although it's more difficult to understand, you'll get the hang of it, but it gives you a better understanding of the molecule you have because there's more detail with it. But carbon-13 NMR is still very useful, and in your exam you don't have to worry about all of that. It'll give you enough information for you to draw out your compound, and you should be getting through carbon-13 NMR generally much more swiftly than hydrogen-1 NMR. So, and it's the only reason why carbon-13 NMR isn't used as much compared to, I mean, from what I understand, it isn't used as much compared to hydrogen-1 NMR, is the reason that I'll get onto later on, quite quickly later on, as you can see here, it will be about abundance. But let's get straight into the video before I start continue waffling on. I'm actually quite annoyed that this didn't work the first time around. But anyway, it is what it is. So we can work out the different carbon-13 environments from the carbon-13 spectra. In the spectra, different chemical shifts represent carbon-13s in different environments. So remember, it's only the isotope carbon-13 that the NMR works for, not the more common carbon-12. Because carbon-13's abundance, as I was trying to get onto, carbon-13's abundance is only 1.1%, and that's very, very low. So remember, and this won't work for carbon-14 for the exact same reason why it won't work for carbon-12, because you need to have an odd nuclear number in order to do NMR. An odd nuclear number allows for there to be an overall spin, whereas if there's an even nuclear number, there's no overall spin, and therefore NMR can't take place. I've already explained why that is when I did the understanding of NMR and overall magnetic fields and all sorts. I've done that in my previous video. I was talking about understanding NMR. I'll leave a link in the description to that video if you need more help with that, with understanding NMR. But in reality, when I've done NMR questions, the majority of the time they're just looking for how you're able to understand the spectra and be able to understand spectra alongside using other information along with the spectra, such as they'll give you many graphs, many spectra. They'll give you an IR spectra. They may even give you mass spec. And they may even give you some chemical tests along with it, just to give you as much information. They won't just give you just the NMR spectra. They give you loads of different types of information, like you would do in a real lab. And then once you you have to use all the information together to help you, and that's a good thing. Having lots of information is a good thing because it helps you understand what type of molecule you have, and kind of condense it down to this type of specific molecule you have, and then be able to use all that information to decide what your compound is, because you have all that information. But yeah, you don't have to know too much about understanding of NMR, but it is part of the specification. So the link to that video is in the description, and it's always just the previous video. Yeah, so there we go. So tetramethylsilane. So tetramethylsilane is used during carbon-13 spectral readings as a reference, and this is used because the chemical shifts along the x-axis are relative to the shift of TMS. TMS, tetramethylsilane, is a good reference since it only produces one peak at 0 ppm because each carbon-13 is in the same environment. So for this reason, lots of spectra will have a single peak at 0 ppm, And remember, this is just for your, this is just your reference peak. Now, so tetramethylsilane is there's other types. There's not just tetramethylsilane. There's another one called CD3. So CD4. I'll get onto why we have tetramethylsilane. I can't already put it here. Really, I've already said it's a reference. You need a reference here. So this little peak here at 0 ppm. That's TMS. That's a reference peak. Now you need that to be able to understand what from which point we're measuring our ppm or our chemical shift for carbon-13 NMR. So from what point we can read onwards. So if it's from here onwards, I shouldn't have used the highlight there. I used a analysis from this point here. We know this to be 0 ppm. Now we know this is 0 ppm, and we can use this as our reference because roughly 0 ppm, because all the carbon-13s in this environment here, of this compound, right? Oh, that's a terrible one to use. All the carbon-13s in this environment all the carbon-13s here in this molecule are in the exact same environment. Think about it, right? Okay, so this is exact same thing as this here, as this here, as this here. The exact same conditions. So therefore they all cancel out. And therefore we know the overall, actually that here is as is. Therefore we know the overall the peak will be at 0 ppm because it'll cancel out. They're all in the exact same environment. And that's what that's why it's such a good reference. Now there's other types of reference compounds you could use, not just TMS. There's another one called the one that I'm thinking of is more for hydrogen 1 NMR, and I'll go through that when I go in that video. But why TMS is good. There's a list of reasons why. This is actually a question in your exam. They'll ask you why is TMS such a good reference. I believe it's because it's non-toxic. It's easy to dissolve, and all the carbon-13s are in the same environment. Look at your mark scheme just in case. I'll probably go through that in I'll leave a note actually. That's actually not what I wanted to use. That is one thing they actually look at during your so that's one question that they like to ask in your exam by NMR. Why is TMS a good reference compound? And one of the reasons, and the most important reason really, is that all the carbon-13s are in the exact same environment, and therefore they would cancel out. So that's why it's good to use as a reference. But there are other reasons. They may ask for 3 reasons, and one of them usually is that the TMS is non-toxic. I believe it's non-toxic. Another one I believe is because it's easily soluble. But look at the mark scheme, and I'll make sure to get back to you on this one when I actually do the next video. And if I forget to do that, leave a comment in the description, and I'll make sure to do that. So carbon-13's example, right? So I've got an example here, right? So carbon-13 NMR for ethanol. So you need to look at a data table, which is in your data sheet, to determine the carbon environments represented by the peaks in the spectrum. So here we have ethanol, right? So I want you to I'm going to go through how I would look at this question, and then kind of go through my reasoning. So this compound is ethanol, and I'm going to go explain to you why. So there's a peak here at 200 ppm, and we look at our data sheet, right? So how would I go through this? Sorry, I forget that you can't see my hands because I'm doing a screen recording rather than a video. You can't see my hand gestures, but I am pointing towards the 200 ppm. So how would I look at this spectrum? How would I use it to identify this compound? Now I already know what the compound is because it's obviously right here. We know it's ethanol, but how would I if this wasn't here, which it won't be obviously, how would I determine its compound? So the first thing I look at is the most obvious one, which is now the beauty of carbon-13 NMR is that when you come down to look at hydrogen 1 NMR, the peaks might be doublets, triplets, and you know what I'll talk about what doublets, singlets, doublets, triplets, what all that is. But all you need to know is that in carbon-13 NMR, it's just one single peak. I'll go back hydrogen 1 NMR later when I do that video, but for carbon-13 NMR, It's all one single peak, so you don't have to worry about any of that. So it's very blatant what it is. If they don't put it like here, they probably won't leave saying it's 31 ppm, but it'll probably be very obvious that's within this range here. If they don't, if they might, they probably would say, but if they don't say it, it should be quite obvious where it is. But anyway, and it'll give you enough information to know how much carbons you have. If they don't have to give you enough information, they'll have enough information to answer the question. That's what I mean. You'll have enough information to answer this question. All right, so how would I answer this question? I'm actually going to stop waffling now and actually go to say, how would I actually answer this question now? So I look at this, 200 ppm. That's the most obvious one here. Like the ones, usually when you get ones around here, around this region, there's quite a lot of them because you may have a lot of carbon single bonds if this is like a longer compound. So I'd usually look at the ones closer to the higher range because they're the ones that are the more obvious ones. So now 200 ppm, right? What does that represent? So 200 ppm, I'm looking here, and there's only one here, and that's an aldehyde. That's the carbonyl group here. Now, be very, 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 very careful. When I first did NMR, I always made this mistake. Now, this is also a carbonyl, but this is the only one that fits the range of between 200 ppm. It's within 190 to 220 ppm, so it's this here. Now, I never made this mistake, but I'd always sometimes skip or just assume that it's an ester because I saw a carbonyl bond or an acid, but it's very important that you mention aldehyde, ketone. And if it's within the range of an ester or acid, ester, acid, or obviously it's not going to be ester. Just say it's going to be one of the two, obviously. But it's going to be either. In this case, we know it's not. We know it's not an ester or acid because our value was within 200 ppm. So it's going to be either an aldehyde or a ketone. Now, usually you have to look more by other compounds to determine whether or not it's an aldehyde or ketone. But here it's very simple. There's only two peaks here. And the peaks represent carbon-13 NMRs. So if there's only two peaks, there's only two carbons within that environment. And therefore, we know that this is obviously, we're assuming all of this as in we don't know what compound this is here, right? I should have rubbed out this, I should have blurred this out. I should have done that instead. But it's too late now for that, really. But yeah, so we know there's only two carbons in this compound because there's only two peaks. Therefore, it can't be a ketone if there's only two carbons. So we know definitely it's an aldehyde. And it's within 190 to 220. So, and the other one here. So now we know that's an aldehyde bond, or for carbonyl for an aldehyde. Let's go and look. What's the 31 ppm represent, right? Now we know that one of them must be. This makes it much now that we know that there's only one other carbon. It makes it much easier for us to cancel out, because there's quite a lot of them between. There's quite a lot of ranges where 31 would fit in. We know it's not this one here. Although 31 is in that range, we know that one of our carbon is bonded to a carbonyl. So our carbon is bonded to a carbonyl, so it can't be that. We know it's not going to be this one, even though 31 is within that range. We have no chlorine or bromine, so it can't be that. It's most likely this one here, because it's bonded to a carbon, and actually it's not most likely, it is this one here, because it's the only one that fits within our range. That's a carbon that's bonded to a carbonyl. So this is the one. Obviously I'm doing this step by step because I know over time, or if you know what's going on, you don't have to wait for me saying each and every single step. You can pretty much see it straightforward. But I'm just kind of going through if this is a much longer compound, try and go through this kind of understanding of it, or this type of method. Obviously it's not this one because you haven't got nitrogen in it, so that's not that. And all the other ones here are outside our range, so we know definitely this is our other carbon-13. So how do they represent this? So they'll usually ask you a question along the lines of explain what the spectra represents and point out to what, or denote what compound this could possibly be based off the carbon-13 spectra. Now I'd say that this compound is ethanol because we have a peak at 200 ppm that represents a carbonyl bond for an aldehyde. That's within the range, because it's within the range of 190 for 220, which is for an aldehyde carbonyl group. And then we have another peak at 31 ppm. That must be a carbon that's bonded to a carbonyl, because it has it's within the range of 20 to 50. It's within the range of 20 to 50 ppm, and it's the only carbon that's bonded to a carbonyl, and therefore that is the other carbon-13 carbon. So that's the other carbon there, and therefore you know that overall our compound must be ethanol, and that's it. So that's how to go through it. Obviously, you get a much longer and difficult question. I'll be going through I'm nearly finished with organic chemistry now. And once I've done that, I'll be able to go and explain to you. Once I've done that, I'll be able to explain to you. Sorry, I'll be able to do exam questions. I was just my brain just kind of got stuck there. Sorry. Well, I'm nearly finished with organic chemistry, and what I usually do when I finish big units, I go through exam questions of each topic. So I'll do exam questions on Carbon-13 if this wasn't clear for you or you didn't think is that useful to you. Again, leave a comment in the description if you didn't think this was useful to you, what I could have done better, or if you did find it useful, leave a like and subscribe, I guess. But I'm gonna do me going through an entire paper of NMR, so you can see how it's done in the exam, and it kind of gives you a bit of an idea of how to answer them, and what to look for, what's the mindset to think about when you're answering questions in the exam. So I'll be doing that video pretty soon. There's only 2 more videos I have to do for NMR, and that's pretty much the end of organic chemistry for me. I've done all the other content. Yeah, it's the end of it's the end of year 2 organic chemistry, and I've already finished year 1 time ago already. So yeah, that's it. Hopefully the video was helpful to you, and that is it.